Hello there, and welcome to Sleep Knowledge. I'm so glad you found your way here. Tonight, we're drifting toward the closest stars to our own. A place so near in cosmic terms, yet so impossibly far by human measure. Alpha Centauri waits out there in the southern sky. A triple star system holding secrets we're only beginning to glimpse. If these calm explorations help you unwind, consider liking and subscribing. It helps others find their way here too. One sleepy soul at a time. Now, let yourself settle in. Take a deep breath, and let's begin. Alpha Centauri isn't a single star. It's a family of 3 stars bound together by gravity, dancing around each other in the darkness. 2 of them, Alpha Centauri A and B, orbit closely, circling each other every 80 years. The third, Proxima Centauri, drifts much farther out, taking over 500,000 years to complete a single orbit around its 2 brighter companions. Think about that for a moment. 3 suns, each with its own character, bound together in a gravitational embrace that has lasted for billions of years. They were born from the same clouds of gas and dust that collapsed under their own weight, igniting fusion in their cores and beginning their long lives as stars. The bond between Alpha Centauri A and B is intimate, cosmic partners locked in an eternal dance. At their closest, they approach each other to within about 11 astronomical units. Imagine placing the Sun where it is, and another sun roughly where Saturn orbits. The light from one star would illuminate the other, casting complex shadows, creating tidal forces that tug at each star's outer layers. At their farthest separation, they drift to about 36 astronomical units apart. Farther than Neptune orbits our Sunday, yet even at this distance, they remain bound, their mutual gravity ensuring they'll never escape each other's pull. The orbit itself is elliptical, not circular. As the 2 stars sweep through space, they speed up when closer together and slow down when farther apart, following the same laws of motion that govern planets. The point around which they orbit, called the barycenter, isn't inside either star, but rather in the empty space between them, positioned according to their masses. Alpha Centauri A, being slightly more massive, pulls the barycenter closer to itself. If you could watch from a great distance, you'd see both stars tracing elliptical paths around this invisible point in space. Neither star truly stationary, both in constant motion. This creates a dynamic, ever-changing environment. Any planets orbiting these stars would experience shifting gravitational forces as the stars moved closer and farther from each other. The amount of light a planet receives would vary over the 80-year orbital cycle. Seasons on such a world wouldn't be determined by the planet's axial tilt alone, but also by the complex interplay of 2 suns. Now imagine being on a planet orbiting Alpha Centauri A. For 40 years, you'd watch Alpha Centauri B grow brighter in the sky as the 2 stars approached each other. At closest approach, B would shine brilliantly, perhaps as bright as several hundred full moons from Earth. The sky would be dominated by 2 suns, one yellow, one orange, their combined light flooding the landscape. Then, over the next 40 years, B would drift away, growing dimmer until it became just another bright star among many, though still far brighter than any star in Earth's night sky. The rhythms of life on such a world would be measured not just in days and years, but in the 80-year cycle of the stars themselves. Entire lifetimes could pass within a single stellar orbit. Generations would witness the stars approach, reach their closest point, and begin to separate again. And all the while, Proxima Centauri would glimmer in the distance, a faint red point of light, so far away that it would barely seem connected to the system at all. From a planet orbiting A or B, Proxima would look like just another star, distinguishable only by its faint reddish color and its fixed position in the sky, relative to the binary pair. Proxima's orbit around A and B is so vast and so slow that measuring it has been a challenge for astronomers. The star moves at a leisurely pace, covering its enormous orbit over more than 500,000 years. At that timescale, human civilization would rise and fall countless times before Proxima completed even one lap around its companions. Some astronomers have questioned whether Proxima is truly bound to Alpha Centauri A and B, or if it's simply passing by, a temporary visitor that will eventually wander off into the galaxy. Current evidence suggests it is bound, but the orbit is so elongated and so slow that certainty is difficult to achieve. Regardless, for now, and for tens of thousands of years to come, Proxima will remain near Alpha Centauri, a distant red companion to the golden binary pair. This triple system lies just over 4 light-years away. That's the nearest star system to our Sunday. In galactic terms, Alpha Centauri is our next-door neighbour, yet in human terms, the distance is staggering. Light, travelling at 186,000 miles per second, still takes more than 4 years to cross the void between us and those stars. Let's put that in perspective. Light can travel from Earth to the Moon in about 1.3 seconds. It reaches Mars in a matter of minutes. It crosses the entire solar system, from the Sun to the orbit of Pluto, in about 5.5 hours. But to Alpha Centauri, 4 years and 4 months of continuous travel at the universe's ultimate speed limit. In more familiar terms, Alpha Centauri is about 25 trillion miles away. That's 25 followed by 12 zeros. If you started driving toward Alpha Centauri in a car at highway speed, traveling day and night without stopping, it would take you more than 40 million years to arrive. If you could somehow travel at the speed of our fastest spacecraft, the Parker Solar Probe, moving at roughly 430,000 miles per hour, the journey to Alpha Centauri would take over 6,700 years. Generations would be born, live, and die aboard that ship before it arrived. Let's imagine what that journey would be like. You launch from Earth, accelerating away from the Sun, building up speed as you go. Eventually, you reach cruising velocity 430,000 miles per hour. At first, you'd still see the Sun behind you, bright and familiar, but day by day, it would grow dimmer, shrinking from a blazing disk to a bright star, then to just another point of light among many. After a few years, the Sun would be indistinguishable from other stars, just one more dot in the cosmic tapestry. You'd be truly alone, farther from home than any human has ever been, drifting through the void between stars. For decades, nothing would change. The stars ahead would remain fixed in their positions, the emptiness around you vast and unchanging. There would be no sense of motion, no landmarks to gauge your progress. Only the passage of time and the slow drain of resources would mark your journey. Generations would pass. The children born on the ship would grow up knowing only the interior of the spacecraft, a world of metal walls and recycled air. They would learn about Earth from stories and images, a distant place they would never see. Their children and their children's children would continue the journey, maintaining the ship, tending the gardens, keeping the mission alive. Knowledge would be passed down through the ages, memories of a home that existed only in history. Finally, after 6,700 years, Alpha Centauri would begin to grow brighter in the viewports. What had been a faint point of light would slowly resolve into 3 distinct stars, 2 golden suns orbiting each other, and a dim red companion nearby. The descendants of the original crew, hundreds of generations removed, would finally arrive at their destination. They would see what no human had ever seen. Another star system up close, worlds orbiting alien suns, landscapes shaped by different stars. But think about what would have happened back on Earth during that time. When the ship launched, civilization would have been at a certain level of technology, a certain stage of development. By the time the ship arrived at Alpha Centauri, 6,700 years later, Earth would have advanced unimaginably. New propulsion technologies might have been developed, allowing faster ships to make the journey in centuries instead of millennia. Those ships might arrive at Alpha Centauri before the original expedition, having launched thousands of years later. This is sometimes called the weight calculation problem. If we send a ship now with current technology, should we wait for better technology to develop, allowing future ships to arrive sooner? There's no perfect answer. We could wait forever, always hoping for the next breakthrough. Or we could launch now, accepting that we're planting seeds for a far future we'll never see. Either way, the journey to Alpha Centauri with current technology remains a commitment measured not in years or decades, but in millennia. Alpha Centauri A the brightest of the three, is remarkably similar to our Sunday. It's only about 10% more massive and about 50% brighter. If you stood on a planet orbiting Alpha Centauri A, its light would feel warm and familiar. Not so different from the sunlight that touches Earth. Alpha Centauri B is slightly smaller and cooler, about 90% the mass of the Sunday. Together, A and B create a binary pair, two stars locked in an eternal cosmic waltz. At their closest approach, they come within about 11 astronomical units of each other, roughly the distance from our Sun to Saturn. At their farthest, they drift apart to about 36 astronomical units. Proxima Centauri, the third member of this stellar family, is a red dwarf, a small, dim star, much cooler than its two companions. It's only about an eighth the mass of the Sun and produces only about 0.17% of the Sun's luminosity. You could hold Proxima in your hand, metaphorically speaking, and it would glow like a hot ember rather than blazing like a furnace. Despite being the dimmest of the three, Proxima Centauri holds a special place in our search for other worlds. In 2016, astronomers discovered a planet orbiting this faint red star. They named it Proxima Centauri B. The discovery came after years of careful observation. Astronomers used a technique called radial velocity measurement, which detects the tiny wobble a planet induces in its star as it orbits. As the planet pulls on the star gravitationally, the star shifts slightly toward and away from us, causing its light to be Doppler, shifted, blue shifted when moving toward us, red shifted when moving away. These shifts are incredibly small, requiring extremely precise instruments to detect. For Proxima Centauri B, the wobble amounts to about 5 km/h walking speed. Detecting such a subtle motion in a star over 4 light-years away is a triumph of modern astronomy. Once the signal was confirmed and validated, astronomers could calculate the planet's mass and orbital period. Proxima Centauri B is roughly Earth-sized, with a minimum mass of about 1.07 times Earth's mass. It orbits its star every 11 days, circling at a distance of just 0.05 astronomical units, far closer than Mercury. Orbits the Sunday. If Proxima B orbited our Sun at that distance, it would be scorched, its surface molten rock baking under the Sun's intense radiation. But because Proxima is so dim and cool, this tight orbit places the planet within the habitable zone, the region where liquid water could exist on a planet's surface. Let's think about what that means. The habitable zone is sometimes called the Goldilocks zone, not too hot, not too cold, but just right for liquid water. Water is essential for life as we know it. It's a solvent that allows chemical reactions to occur, a medium that transports nutrients and waste, a stabilizer for temperature. On Earth, wherever we find liquid water, we find life. From the deepest ocean trenches to subglacial lakes in Antarctica, from desert oases to hydrothermal vents, life thrives in the presence of water. The fact that Proxima B orbits within the habitable zone doesn't guarantee it has water or life, but it means the conditions might be right. If the planet has an atmosphere, if it has the right geological activity, if it has protection from stellar radiation, then liquid water could exist on its surface. And if liquid water exists, then the possibility of life, however remote, becomes real. But Proxima Centauri is not a gentle star. It's prone to violent flares, sudden eruptions of energy that can increase the star's brightness by several times in a matter of minutes. These flares release torrents of ultraviolet and X-ray radiation, as well as charged particles that stream outward in all directions. For a planet orbiting as close as Proxima B, these flares would be catastrophic if the planet lacked protection. Without a strong magnetic field to deflect the incoming particles, and without a thick atmosphere to absorb the radiation, the surface would be bombarded with harmful energy. Earth's magnetic field protects us from the solar wind, channeling charged particles toward the poles where they create the auroras, shimmering curtains of light in the Arctic and Antarctic skies. Mars, which lost most of its magnetic field billions of years ago, has had much of its atmosphere stripped away by the solar wind over time. Does Proxima B have a magnetic field? We don't know. To generate a magnetic field, a planet typically needs a molten, electrically conductive core that's in motion. Earth has this, a liquid iron core rotating and churning, creating the magnetic dynamo that shields us. Whether Proxima B has such a core depends on its composition and internal heat. Rocky planets of similar size to Earth could have active cores, or they could have cooled and solidified long ago, leaving them magnetically inert. Without direct measurements, we can only speculate. But the question is crucial, because it determines whether Proxima B could hold onto an atmosphere over billions of years, or whether it would be stripped bare by its star's fury. Then there's the question of the atmosphere itself. Does Proxima B have one? And if so, what is it made of? On Earth, our atmosphere is about 78% nitrogen, 21% oxygen, and trace amounts of argon, carbon dioxide, and other gases. The oxygen is produced by photosynthetic life plants, algae, and cyanobacteria that split water molecules and release oxygen as a waste product. Before life began producing oxygen, Earth's atmosphere was very different, composed mainly of nitrogen, carbon dioxide, methane, and water vapor. Over billions of years, photosynthetic organisms transformed the atmosphere, making it breathable for complex life like us. If Proxima B has an atmosphere, it might be similar to early Earth, thick with carbon dioxide and nitrogen, perhaps with methane or ammonia. Or it might be utterly alien, composed of gases we haven't even considered. Alternatively, it might have no atmosphere at all. The flares from Proxima could have eroded any gases the planet once had, leaving a barren, airless rock like Mercury. Astronomers are working to answer these questions using powerful telescopes like the James Webb Space Telescope. By observing Proxima B as it passes in front of or behind its star events called transits and occultations, they can analyze the starlight filtering through the planet's atmosphere, looking for the chemical signatures of specific gases. If they detect water vapor, that would be a strong hint that the planet has retained an atmosphere and possibly liquid water on its surface. If they find oxygen or methane, especially in combination, that would be even more intriguing, as these gases can be produced by biological processes. But Proxima B might not transit its star from our perspective. Transits only occur if the planet's orbit is aligned edge-on to our line of sight, which happens randomly. If the orbit is tilted, we'll never see the planet cross in front of its star, making atmospheric studies much harder. Still, even without transits, astronomers can learn a lot. They can study the light reflected from the planet's surface, looking for signs of oceans, clouds, or ice. They can measure the planet's temperature and search for seasonal variations that might indicate weather patterns. Every piece of data brings us closer to understanding what Proxima B is really like: a rocky desert, a water world, a toxic wasteland, or perhaps, just perhaps, a place where life has taken hold. Imagine if we confirmed the presence of life on Proxima Centauri B. Not intelligent life, necessarily, but even microbial life would be profound. It would mean that life is not unique to Earth, that the processes that gave rise to biology here have occurred elsewhere, independently. It would suggest that life is common in the universe, that wherever the conditions are, right liquid water, chemical ingredients, energy sources, life will emerge. And if life is common, then perhaps intelligent life is too, waiting to be discovered among the stars. Or maybe we'd find that Proxima B is lifeless, a harsh world scoured by radiation, its surface sterile and silent. That too would teach us something about the fragility of life, about the narrow range of conditions required for biology to flourish, about how rare and precious Earth might be. Either answer changes how we see ourselves and our place in the cosmos. For now, Proxima Centauri B remains a mystery, a world we can see only as a data point, a wobble in starlight, a possibility hanging in the darkness. But that's enough. The fact that it exists, that there's a rocky planet orbiting the nearest star to our own, is itself extraordinary. It's a reminder that planets are everywhere, that the galaxy is full of worlds, each with its own story. Some might be barren rocks, some might be gas giants swirling with storms, and some, just maybe, might be oases of life, sheltered beneath alien skies. Beyond Proxima B, astronomers suspect there may be other planets in the Alpha Centauri system, observations hint at possible worlds orbiting Alpha Centauri A and B, though these detections remain tentative, requiring further confirmation. The search continues. The challenge of finding planets around Alpha Centauri A and B is significant. Both stars are bright, which makes it difficult to detect the faint signals of planets. The stars also orbit each other, creating complex gravitational dynamics that can mask or mimic planetary signals in the data. Still, astronomers persist. Using increasingly sophisticated instruments and techniques, they search for the tiny wobbles planets would induce in their host stars, and for the slight dimming that occurs when a planet passes in front of its star from our perspective. There have been tantalizing hints. In 2012, astronomers announced the detection of an Earth-sized planet orbiting Alpha Centauri B. But this discovery was later called into question when other teams couldn't confirm it. The signal might have been real, or it might have been an artifact of the data, a ghost in the noise. More recently, observations have suggested the possible existence of a planet orbiting Alpha Centauri A, potentially in the habitable zone. But again, confirmation is difficult, and the scientific community remains cautious. What we do know is that planets are common. Nearly every star we've studied in detail has planets. From small, rocky worlds to massive gas giants, there's no reason to think Alpha Centauri A and B would be exceptions. If planets exist around these sun-like stars, they might be more hospitable to life than Proxima B. Alpha Centauri A and B don't experience the violent flares that plague Proxima. Their light is warmer, brighter, more like the sunlight that nourishes life on Earth. A planet in the habitable zone of Alpha Centauri A would receive sunlight very similar to what Earth receives. Days and nights would follow a familiar rhythm. The sky would be blue, not red. Plants could photosynthesize using mechanisms similar to those on Earth, and from such a planet, the view would be spectacular. Alpha Centauri B would shine in the sky like an incredibly bright star, perhaps 10 times brighter than Venus appears from Earth. It would cast shadows, illuminate the night, a constant companion star sharing the heavens. During the day, with Alpha Centauri A overhead, B would be visible as well, a brilliant point of light in the blue sky. You could see both suns at once, a reminder that this is not a solitary system like our own, but a family of stars. The idea of traveling to Alpha Centauri has fascinated humanity for decades. In the 1970 seconds, the British Interplanetary Society designed a theoretical spacecraft called Project Daedalus. It would have used nuclear pulse propulsion, essentially detonating small nuclear bombs behind the ship to accelerate, and could theoretically reach Alpha Centauri in about 50 years. Project Daedalus was never built, but the design was remarkably detailed. The spacecraft would have been enormous, about 60,000 tons at launch, most of that mass being fuel. It would use pellets of deuterium and helium-3 as fuel, ignited by electron beams to create controlled fusion explosions. Each explosion would propel the ship forward, adding to its velocity. Over the course of 4 years of continuous thrust, Daedalus would accelerate to about 12% the speed of light, roughly 22,000 miles per second. At that speed, it could cross the distance to Alpha Centauri in about 50 years. But there were problems. Helium-3 is extremely rare on Earth, found only in trace amounts. The mission would require mining it from the atmospheres of gas giants like Jupiter, an engineering challenge beyond anything we've attempted. The spacecraft would also need to carry massive radiation shielding to protect its instruments from the harsh environment of interstellar space. And perhaps most challenging of all, Daedalus had no way to slow down. It would zip through the Alpha Centauri system in a matter of days or weeks, gathering data as fast as possible before continuing into the void beyond. There would be no orbiting, no lingering, no detailed study, just a high-speed flyby, and then silence. Still, Project Daedalus proved that interstellar travel was physically possible. Even if monumentally difficult, it laid the groundwork for future concepts and inspired generations of scientists and engineers to think seriously about reaching the stars. More recently, the Breakthrough Starshot initiative proposed a different approach. Tiny spacecraft, equipped with light sails, propelled by powerful lasers from Earth. These miniature probes, weighing just a few grams, could accelerate to 20% the speed of light, reaching Alpha Centauri in about 20 years. They wouldn't slow down, they'd fly past at incredible speed, capturing data and images before continuing into the void. The concept is elegant in its simplicity. Each probe would consist of a lightweight microchip attached to a thin, reflective sail made of ultralight material. An array of powerful lasers on Earth would focus their beams on the sail, pushing it with the pressure of light itself. Light has momentum, even though it has no mass. When photons strike a reflective surface, they bounce off, transferring momentum to the surface. It's a tiny effect, you don't feel light pushing on you, but over time, in the vacuum of space, this gentle pressure can accelerate a lightweight object to incredible speeds. Breakthrough Starshot envisions a laser array with a combined power output of about 100 gigawatts, roughly the output of 100 large nuclear power plants. This array would fire continuously at the probe's sail for about 10 minutes, accelerating it from rest to 20% light speed. Then the lasers would shut off, and the probe would coast, gliding through space at a fifth the speed of light, covering the distance to Alpha Centauri in about 20 years. But even this seemingly simple concept is filled with challenges. Building a 100 gigawatt laser array is an extraordinary engineering feat. The lasers would need to be precisely coordinated, their beams combining into a single focused point that tracks the sail as it accelerates away. The atmosphere would distort the laser beams, scattering and absorbing some of their energy. Adaptive optics systems that correct for atmospheric distortion in real time would be essential, similar to the technology used in modern telescopes. And the sail itself would need to be impossibly thin and light, yet strong enough to withstand the intense laser pressure without tearing or vaporizing. It would need to be perfectly reflective, bouncing back as much light as possible to maximize the acceleration. Then there's the problem of what happens when the probe reaches Alpha Centauri. Traveling at 20% light speed, it would cross the entire star system in a matter of hours. It would have only a brief window to capture images and data before it was gone, racing past into interstellar space. The data would need to be transmitted back to Earth using a tiny laser or radio transmitter, powered by the probe's even tinier power source. The signal would be incredibly faint by the time it reached Earth, requiring massive receivers to detect it. And all of this assumes the probe survives the journey. Interstellar space is not completely empty. It contains hydrogen atoms, dust grains, and other particles, sparse but present. At 20% light speed, even a collision with a single grain of dust would be catastrophic, releasing energy equivalent to a small bomb. Shielding the probe is nearly impossible, because adding mass defeats the purpose. The whole design depends on being ultra-lightweight. Some proposals suggest using the sail itself as a shield, positioning it ahead of the probe to absorb impacts. But this would degrade the sail over time, potentially rendering it useless long before the probe reaches its destination. Despite these challenges, Breakthrough Starshot is more than just a thought experiment. It's a serious initiative backed by funding and research, with scientists and engineers actively working to solve the technical problems. If successful, it could send humanity's first emissary to another star system within our lifetimes. Imagine receiving data from Alpha Centauri 20 years after launch. Images of Proxima Centauri B, taken from just thousands of miles away, showing details invisible from Earth. Measurements of its atmosphere, its magnetic field, its surface temperature. Glimpses of the binary suns, Alpha Centauri A and B, their surfaces mapped, their dynamics revealed. It would be a moment of triumph, a confirmation that we can reach beyond our solar system, that the stars are not forever out of reach, and it would be just the beginning. If we can send tiny probes to Alpha Centauri, we can send them to other nearby stars too. Barnard's star, Luton's star, Wolf 359, all within 10 light-years. Over time, we could build a network of data from dozens of nearby star systems, mapping the galactic neighborhood, identifying the best candidates for future exploration, perhaps even finding signs of life among the stars. This is the vision that drives projects like Breakthrough Starshot, not just to reach Alpha Centauri, but to take the first step toward becoming a truly spacefaring civilization. one that doesn't just dream of the stars but actually visits them. But even these ambitious concepts remain theoretical. The engineering challenges are immense. Accelerating anything to a fraction of light speed requires energy on a scale we've never harnessed. Protecting a spacecraft from interstellar dust and radiation at such velocities is another problem entirely, and communicating across 4 light years means that any message sent home would take over 4 years to arrive. Still, the dream persists. Alpha Centauri is close enough to imagine reaching, yet far enough to test the very limits of human ingenuity and ambition. The stars of Alpha Centauri have been known to humanity for thousands of years, visible from the southern hemisphere as a single bright point of light. Ancient cultures would have seen it in their skies, woven it into their myths, used it to navigate. It wasn't until the early 1800s that astronomers realized this single star was actually 2. Using telescopes, they observed that the light separated into 2 distinct points, Alpha Centauri A and B. Proxima Centauri, too faint to see with the naked eye, wasn't discovered until 1915. For much of the 20th century, Alpha Centauri remained a curiosity, a nearby stellar system useful for studying stellar properties and dynamics. But the discovery of exoplanets changed everything. Suddenly, our neighboring stars weren't just distant suns, they were potential homes for other worlds, perhaps even other life. The name Alpha Centauri comes from the Bayer designation system, developed in the early 17th century by German astronomer Johann Bayer. This system labels stars by brightness within their constellation, using Greek letters: Alpha for the brightest, Beta for the second brightest, and so on. Alpha Centauri is the brightest star in the constellation Centaurus, the Centaur. In Arabic, the system is sometimes called Rigil Kentaurus, meaning the foot of the Centaur. From Earth, Alpha Centauri appears as a single yellowish star, one of the brightest in the night sky. But only from the southern hemisphere can you see it well. Those living north of about 25 degrees latitude will find it perpetually below the horizon, forever out of view. If you were standing on Proxima Centauri B, looking up at the sky, what would you see? Proxima Centauri would dominate the heavens, a deep red sun, larger in apparent size than our sun appears from Earth. It would cast a dim, reddish light across the landscape, painting everything in hues of crimson and shadow. In the distance, Alpha Centauri A and B would shine brilliantly. 2 bright stars close together, like binary headlights in the cosmic dark. They would be the brightest stars in Proxima B's sky, far brighter than any star appears from Earth. They would never set, forever visible, eternal companions to the red dwarf sun. Now, let's drift to the science of red dwarfs, the smallest and most common type of star in the galaxy. Proxima Centauri is one of these faint, long-lived stars. Red dwarfs burn their hydrogen fuel so slowly that they can shine for trillions of years, far longer than the current age of the universe. To understand why, we need to think about how stars work. A star is fundamentally a battle between 2 opposing forces: gravity, which pulls matter inward, and pressure, which pushes outward. At the star's core, hydrogen nuclei are slammed together with such force that they fuse into helium, releasing tremendous energy in the process. This energy creates pressure that holds the star up against gravity's relentless pull. Massive stars burn hot and fast. Their cores are furnaces running at millions of degrees, fusing hydrogen at an incredible rate. They shine brilliantly, but their fuel is exhausted in mere millions of years. When the hydrogen runs out, these massive stars swell into red supergiants, then explode as supernovae, scattering their remains across space. Our Sun, a medium-sized star, has a more measured pace. It's been shining for about 4.6 billion years and has enough hydrogen left to continue for another 5 billion. When its fuel finally runs low, the Sun will expand into a red giant, engulfing Mercury and Venus, perhaps even Earth. Then it will shed its outer layers, creating a beautiful planetary nebula, while its core collapses into a white dwarf, a hot, dense ember about the size of Earth. But red dwarfs like Proxima Centauri are different. They're so small and cool that their fusion rates are incredibly slow. They sip their hydrogen fuel rather than gulping it down. And because they're fully convective, meaning their interiors are constantly mixing, bringing fresh hydrogen from the outer layers down to the core, they can use nearly all of their hydrogen before running out. A red dwarf can shine for 10 trillion years or more. That's about 700 times longer than the current age of the universe, which is roughly 13.8 billion years. Proxima Centauri, which has been shining for about 4.8 billion years, has barely aged. It's like a candle that just started burning, with 99.99% of its wax still intact. This extraordinary longevity has profound implications for the search for life. Life on Earth took billions of years to evolve from simple, single-celled organisms to complex multicellular life. Intelligence took even longer. Modern humans emerged only in the last few 100,000 years, a blink of an eye in Earth's 4.5 billion year history. If a planet orbits a red dwarf in its habitable zone and remains stable, life would have an almost limitless amount of time to evolve. There would be no rush, no looming deadline when the star's fuel runs out. Life could experiment, diversify, adapt, perhaps eventually reaching levels of complexity and intelligence far beyond anything we've imagined. Of course, this assumes the planet can remain habitable for that long. A red dwarf's habitable zone is very close to the star because the star is so dim. This proximity means the planet would likely become tidally locked, with one side always facing the star and the other side perpetually dark. But red dwarfs present challenges. Many, like Proxima, are prone to violent flares, sudden eruptions of energy that can increase a star's brightness by several times in a matter of minutes. These flares release torrents of ultraviolet and X-ray radiation, as well as charged particles that stream outward in all directions. Young red dwarfs are especially active, flaring frequently and violently. As they age, they gradually calm down, though they never become completely quiescent. Proxima Centauri, despite being billions of years old, still unleashes powerful flares regularly. For a planet orbiting close to a red dwarf, these flares could be catastrophic. Without a strong magnetic field to deflect the incoming particles, and without a thick atmosphere to absorb the radiation, the surface would be bombarded with harmful energy. Yet some scientists argue that life might find a way. On Earth, extremophiles, organisms that thrive in extreme conditions, survive in environments once thought uninhabitable. Deep-sea hydrothermal vents, acidic lakes, frozen Antarctic ice life has claimed them all. Perhaps life on a flare-prone world could shelter underground, emerging only during calm periods, or develop biochemical defenses against radiation. Certain bacteria on Earth can withstand radiation doses thousands of times higher than would kill a human. They have evolved repair mechanisms that can fix DNA damage caused by radiation almost as fast as it occurs. Perhaps life on Proxima B, if it exists, has evolved similar or even more advanced defenses. Life might also find refuge in subsurface oceans, shielded from the star's flares by kilometers of ice or rock. On Earth, entire ecosystems exist in lightless depths, sustained not by photosynthesis, but by chemical energy from hydrothermal vents. Similar ecosystems might exist on Proxima B, hidden beneath the surface, oblivious to the storms raging overhead. Or perhaps life on Proxima B, if it exists, thrives on the energy released by the flares themselves. Just as Earth's early life may have been sustained by lightning and volcanic activity, life on a red dwarf planet might harness the chemical reactions triggered by stellar flares. The truth is, we don't know. And that uncertainty is part of what makes Proxima Centauri B so compelling. Red dwarfs also have another fascinating characteristic. They eventually become blue dwarfs, a theoretical phase of stellar evolution that hasn't yet been observed because the universe isn't old enough for any red dwarf to have reached it. As a red dwarf ages and exhausts the hydrogen in its core, it will begin to burn hydrogen in a shell around the core. This shell burning will cause the star to heat up and increase in luminosity. Paradoxically, the star will grow hotter and bluer as it nears the end of its life, becoming a blue dwarf. Eventually, even the shell hydrogen will be exhausted, and the star will collapse into a white dwarf. But this won't happen for trillions of years, long after the Sun and all other stars like it have died. In the far future, red dwarfs will be the last stars shining in a cold, dark universe. Galaxies will have merged and dispersed. Black holes will have swallowed much of the remaining matter, and the cosmos will be a vast, empty expanse. But red dwarfs will still glow, faint embers in the darkness, the final witnesses to a universe slowly winding down toward heat death. And if any civilizations survive to that distant age, they will cluster around red dwarfs, the only sources of warmth and light in an otherwise frozen void. Let's consider the orbital mechanics of the Alpha Centauri system. Alpha Centauri A and B orbit their mutual center of mass, a point in space determined by their relative masses. This barycenter shifts slightly as the stars move, tracing elliptical paths. The gravitational influence of these two stars creates a complex environment for planets. Any world orbiting too close to one star might be destabilized by the gravity of the other. Conversely, planets orbiting farther out might find stable orbits where the gravitational forces balance. Simulations suggest that planets could exist in stable orbits around Alpha Centauri A or B individually, or in wide orbits around both stars together. Proxima Centauri, drifting far from its companions, likely has its own isolated system of planets, minimally influenced by A and B. Astronomers continue to search for planets in this system using techniques like radial velocity measurements, which detect the tiny wobbles a planet induces in its star as it orbits, and transit photometry, which looks for the slight dimming of starlight as a planet passes in front of its star. Finding planets around Alpha Centauri A and B is difficult. The stars are bright, and the signal from a small planet is faint, easily lost in the noise of stellar activity and instrumental limitations. But the search continues, driven by the tantalizing possibility of Earth-like worlds on our doorstep. Now, imagine a future where humanity develops the technology to send a probe to Alpha Centauri. The spacecraft launches from Earth, accelerating for years until it reaches cruising speed. Decades pass. The probe crosses the vast empty space between stars, a tiny speck of metal and electronics hurtling through the void. Finally, it enters the Alpha Centauri system. Cameras activate. Instruments begin recording data. The probe passes Proxima Centauri first, capturing images of Proxima B, a rust-colored world, perhaps dotted with dark oceans, perhaps wrapped in thick clouds. Flares from Proxima light up the probe's sensors, brief flashes of radiation captured in milliseconds. The probe continues, gliding toward Alpha Centauri A and B. It passes between them, mapping their surfaces, analyzing their light, searching for planets. Every measurement, every image, is compressed and transmitted back to Earth, a message that will take over 4 years to arrive. And when it does, humanity will see its neighboring stars not as distant points of light, but as real places, with landscapes and atmospheres and histories of their own. That future may be closer than we think. Technology advances quickly. What seems impossible today might be routine in a century. And Alpha Centauri, our nearest stellar neighbor, will be waiting. Let's turn our thoughts to the nature of starlight. The light we see from Alpha Centauri began its journey over 4 years ago. When you look up at that bright yellowish star in the southern sky, you're seeing the system as it was in the past. Proxima Centauri's faint glow, invisible without a telescope, left its surface during a time you may not even remember. This is true of all stars. The light from Sirius, the brightest star in our sky, is about 9 years old by the time it reaches us. Betelgeuse, that red giant in Orion, shines with light over 500 years old. We see the universe not as it is, but as it was. And yet, in cosmic terms, 4 years is nothing. The light from galaxies billions of light years away reveals the universe as it was in its infancy, long before Earth or the Sun existed. Compared to that, Alpha Centauri is practically a neighbor calling from next door. The Alpha Centauri system is moving through space, as all stars do. It's traveling toward us, slowly closing the distance. In about 30,000 years, it will reach its closest approach to the Sun, a little under 3 light-years away. After that, it will begin to drift away, receding into the galaxy. This motion is called proper motion, and it's a reminder that the stars are not fixed points painted on a celestial sphere. They're real objects moving through 3-dimensional space, each following its own path through the galaxy. From our perspective, Alpha Centauri appears to drift across the sky at a rate of about 3.7 arcseconds per year, a tiny motion, but measurable with precise instruments. Over centuries and millennia, this motion adds up, slowly changing the patterns of the constellations. This slow cosmic dance is part of the motion of stars within the Milky Way. Stars orbit the galactic center, their paths influenced by the gravity of billions of other stars, clouds of gas and dust, and the dark matter that binds the galaxy together. Our Sun, along with Alpha Centauri and countless other stars, traces a path through the galaxy that will take hundreds of millions of years to complete. In that time, the neighborhood changes. Stars that are close now will drift apart. New stars will wander near. The constellations themselves will shift and deform, unrecognizable over deep time. But for now, for our brief moment in cosmic history, Alpha Centauri is near. And that nearness offers hope a chance, however slim, that we might one day reach out and touch another star. Let's think about the colors of stars. Alpha Centauri A shines with a warm yellowish light. Similar to the Sunday, Alpha Centauri B is slightly more orange, its cooler surface giving it a different hue. Proxima Centauri glows deep red, like dying coals. These colors are determined by temperature. Hotter stars emit more blue light, appearing white or bluish to our eyes. Cooler stars emit more red light, appearing orange or red. Our Sun sits in the middle of this range, emitting a balanced spectrum that we perceive as yellowish white. The temperature of a star's surface is linked to its mass. More massive stars burn hotter and brighter, exhausting their fuel quickly. Less massive stars burn cooler and dimmer, conserving their fuel for eons. Proxima Centauri, small and cool, will outlive its brighter companions by an incomprehensible margin. Long after Alpha Centauri, A and B have collapsed into white dwarfs dense, Earth-sized remnants glowing faintly in the darkness. Proxima will still shine, a dim red ember in a galaxy growing ever colder and darker. Now, let's drift to the question of communication. If intelligent life exists in the Alpha Centauri system, could we communicate with them? The answer is yes, technically. Radio waves and light travel at the speed of light, meaning a message sent from Earth would reach Alpha Centauri in just over 4 years. A reply would take another 4 years to return. A conversation would be slow, each exchange requiring nearly a decade, but it would be possible. In fact, humanity has already attempted this. In 2017, humans transmitted a coded radio message from the EISCAT antenna in Tromsø, Norway, aimed at Luiten's star, also known as GJ 273, about 12.4 light-years away. The message contained music and scientific information, encoded in a format designed to be decipherable by an alien intelligence. It should arrive around 2030. If anyone is listening, and if they choose to reply, we might receive an answer roughly 25 years after the original transmission. The likelihood of a response is, of course, vanishingly small. We have no evidence that life exists on Proxima Centauri B, let alone intelligent life capable of receiving and interpreting radio signals. But the act of sending the message is itself meaningful, a gesture of hope and curiosity, a declaration that we are here and we are listening. The search for extraterrestrial intelligence, or SETI, has been scanning the skies for decades, listening for artificial signals from other civilizations. Alpha Centauri is a prime target for these searches. Its proximity and the presence of potentially habitable planets make it a logical place to look. So far, no signals have been detected, but the search continues. Refining techniques, expanding the range of frequencies monitored, hoping that one day, a pattern will emerge from the noise, a message from across the stars. Let's imagine what a signal from Alpha Centauri might mean. It would be proof, undeniable and profound, that we are not alone in the universe. It would reshape our understanding of life, intelligence, and our place in the cosmos. It would also raise questions. How advanced is this civilization? What do they know that we don't? What would we say in return? Some worry about the risks of contact, that revealing our presence might invite danger from a more advanced species. Others argue that any civilization capable of interstellar communication would likely have long outgrown the primitive impulses of conquest and aggression. We don't know. We can only speculate, and hope, and listen. Now, let's turn our thoughts to the physics of interstellar travel. Reaching Alpha Centauri is not just a matter of building a faster rocket. The distances involved are so vast that conventional propulsion simply won't work. Chemical rockets, like those used to launch spacecraft today, are far too slow. Even nuclear propulsion, which would be vastly more powerful, would still require centuries to reach Alpha Centauri. The breakthrough Starshot concept, with its light sails and laser propulsion, offers a glimpse of what might be possible. The idea is to accelerate a tiny probe to 20% the speed of light using a powerful laser array on Earth. The probe would unfurl a reflective sail, and the laser would push against it, accelerating the probe over a matter of minutes to incredible speeds. But this approach has limitations. The probe would be tiny, just a few grams, severely limiting the instruments it could carry. And because it couldn't slow down, it would zip through the Alpha Centauri system in mere hours, gathering data on the fly before continuing into deep space. Another concept involves antimatter propulsion. When matter and antimatter collide, they annihilate each other, releasing enormous amounts of energy. A spacecraft powered by antimatter could theoretically achieve a significant fraction of light speed. The problem is producing and storing antimatter. It's incredibly difficult and expensive to create, and storing it without letting it touch normal matter, causing an explosion, is an unsolved challenge. Still, these ideas are not science fiction. They're based on real physics, real engineering. The barriers are technological, not fundamental, and technology, as history shows, has a way of advancing beyond what we thought possible. Then there's the concept of a generation ship, a massive spacecraft designed to support a human crew for the centuries-long journey to Alpha Centauri. The ship would be a self-contained world, with farms, habitats, artificial gravity, and all the systems needed to sustain life. Generations would be born aboard the ship, live their entire lives in transit, and die before reaching their destination. Only their distant descendants would see Alpha Centauri up close, stepping onto new worlds beneath alien suns. It's a romantic notion, and a profoundly challenging one. The social, psychological, and technical hurdles are staggering, yet it captures something essential about humanity, our drive to explore, to reach beyond the known, to claim new horizons. Let's think about the energy required for such a journey. Accelerating even a small spacecraft to a fraction of light speed requires energy on a scale we don't currently possess. The laser array for breakthrough Starshot, for example, would need to be extraordinarily powerful, on the order of 100 gigawatts, roughly the output of 100 nuclear power plants. Sustaining that energy output for the minutes needed to accelerate the probe would be a monumental engineering feat. And that's just for a tiny probe. A crewed spacecraft would require far, far more energy. But the universe is vast, and energy is abundant. The sun pours out energy at a rate of about 400 trillion watts every second of every day. If we could capture even a tiny fraction of that output, interstellar travel might become feasible. Concepts like Dyson spheres, megastructures that surround a star to harvest its energy, are speculative, but they point to the kinds of solutions future civilizations might develop. If humanity survives and thrives, perhaps one day we'll build such things, and Alpha Centauri will be within reach. Now, let's drift back to the planets. Proxima Centauri B is not the only world suspected to orbit Proxima. Astronomers have found hints of a second planet, tentatively called Proxima C, orbiting much farther out. If it exists, Proxima C would be a super-Earth, several times more massive than our planet, and likely far too cold to support life. Additional candidates have been suggested around Alpha Centauri A and B. Though these detections remain unconfirmed, the complexity of the binary system makes planet detection difficult, as the gravitational interactions between the two stars create noise in the data. But the search goes on. New telescopes, new techniques, and new missions dedicated to studying nearby stars will continue to refine our understanding of the Alpha Centauri system. One day, We may have a complete census of worlds in that system: rocky planets, gas giants, icy moons, perhaps even asteroid belts and comet clouds. We'll know their sizes, their compositions, their atmospheres. We'll know if any of them could harbor life, and if they do, the implications will be profound. Let's consider what habitable really means. The habitable zone, sometimes called the Goldilocks zone, is the region around a star where temperatures are just right for liquid water to exist on a planet's surface. Too close to the star, and water boils away. Too far, and it freezes. But habitability is more complex than just temperature. A planet also needs an atmosphere to retain heat and protect its surface from radiation. It needs a magnetic field to shield it from stellar wind. It needs geological activity to recycle nutrients and regulate climate over long timescales. Proxima Centauri B checks some of these boxes, but not necessarily all. We don't know if it has an atmosphere, or a magnetic field, or active geology. We don't know if its surface is dry rock, deep ocean, or something else entirely. What we do know is that it's the right size and in the right place. The James Webb Space Telescope, launched in 2021, has the capability to study the atmospheres of exoplanets, analyzing the starlight that filters through a planet's air to reveal its chemical composition. Proxima Centauri B is a target for such studies. If Webb or other telescopes detect oxygen, methane, or other biosignature gases in Proxima B's atmosphere, it would be a tantalizing hint of life. Not proof there are non-biological ways to produce these gases, but a strong indicator that something interesting might be happening on that distant world. Now, picture this. A planet orbiting a red dwarf, its one face forever turned toward its star, the other locked in eternal darkness. This is called tidal locking, and it's likely the fate of Proxima Centauri B. Tidal locking occurs when a planet's rotation period matches its orbital period, so the same hemisphere always faces its star. The Moon is tidally locked to Earth, we only ever see one side of it. For a planet like Proxima B, tidal locking creates a world of extremes. The day side, perpetually bathed in red light, might be scorching hot. The night side, forever in shadow, might be frozen solid. In between, along the terminator, the boundary between day and night temperatures might be just right for liquid water. Life, if it exists on such a world, might cluster in that narrow habitable band, where the light is dim but steady, and the temperature remains tolerable. Imagine standing on the terminator of Proxima B. Behind you, the eternal twilight gives way to complete darkness, a frozen wasteland where no light has ever shone. Ahead of you, the landscape brightens into a crimson day, the small red sun hanging motionless in the sky, never rising, never setting. The temperature would be moderate here, cool but not freezing, warm but not scorching. Liquid water could flow, pooling in low-lying areas, forming rivers and lakes that snake along the terminator zone. Above, the sky would be a deep, dusky red near the sun, fading to black at the zenith. Stars would be visible even during the day, scattered across the dark sky, like diamonds on velvet. The air, if there is air, might shimmer with strange optical effects as light bent through temperature gradients. And in the distance, perhaps you'd see storms, great cyclones, driven by the temperature difference between the day and night sides. Winds howling from the scorched day side toward the frozen night side, carrying heat and moisture with them. But that's assuming Proxima B has an atmosphere thick enough to redistribute heat. If it doesn't, the terminator zone might be the only habitable region on the entire planet, a narrow ring encircling the world where temperatures remain in the sweet spot for liquid water. Life adapted to such conditions would be unlike anything on Earth. Plants, if they exist, might not photosynthesize at all. Red light carries less energy than the broad spectrum of sunlight we're used to. Instead, they might rely on chemosynthesis, harvesting energy from chemical reactions in the soil or water, just like the bacteria that thrive around deep-sea vents. Or perhaps life on the day side has adapted to the constant red illumination, evolving pigments that absorb red light efficiently. These organisms might be dark, purple, or black, maximizing their absorption of every photon that reaches them. On the night side, in the eternal darkness, life might exist in subsurface oceans, warmed by the planet's internal heat. These lightless seas could teem with strange creatures, never seeing the stars, never knowing the concept of day or night, living in a timeless realm lit only by bioluminescence, and perhaps, just perhaps, some organisms migrate between the zones. Creatures adapted to the Terminator might venture into the dayside during calm periods, when flares are less frequent, retreating to the twilight when the star erupts. Others might burrow into the night side during the day, emerging in the permanent darkness to feed on nutrients carried by winds from the dayside. It's all speculation, of course. We don't know if Proxima B has an atmosphere, or oceans, or life, but the physics of tidal locking is real, and the implications are fascinating. Or perhaps Proxima B has a thick atmosphere, one that redistributes heat from the day side to the night side, moderating temperatures across the entire surface. In that case, the whole planet might be habitable, or at least survivable. Earth's atmosphere does this to some extent. The tropics receive more sunlight than the poles, but ocean currents and atmospheric circulation redistribute that heat, keeping the poles from freezing completely and the tropics from becoming unbearably hot. On a tidally locked planet, the circulation would be even more extreme. Hot air rising from the day side would flow toward the night side at high altitude, cool and descend, then flow back along the surface as a massive, planet-wide wind. This convection cycle would transfer heat continuously, warming the night side and cooling the day side. If Proxima B has such an atmosphere, the result might be a world where temperatures are moderate almost everywhere. The day side would be warm but not scorching, the night side cold but not frozen. Life could potentially thrive across much of the surface, adapted to the eternal day on one hemisphere and the eternal night on the other. But maintaining such an atmosphere would be challenging. Proxima Centauri's flares would constantly bombard the planet with radiation and charged particles, eroding the atmosphere over time. Only a strong magnetic field could prevent this, channeling the particles harmlessly around the planet and into space. Whether Proxima B has that magnetic field remains one of the great unknowns, a question we'll need better observations to answer. Let's think about the color of the sky on Proxima Centauri B. On Earth, our sky is blue because of the way our atmosphere scatters sunlight. Shorter wavelengths, blue and violet, scatter more than longer wavelengths, like red and yellow. This is called Rayleigh scattering, and it's why the sky appears blue during the day, and why sunsets are red when the sun is low on the horizon. Its light travels through more atmosphere, scattering away most of the blue and leaving the red. On Proxima B, under a red dwarf sun, the sky might have a very different hue. If the planet has an atmosphere similar to Earth's, the scattering of red light would be less pronounced, and the sky might appear darker, tinged with deep crimson or even black. But the atmospheric composition would matter enormously. An atmosphere rich in nitrogen and oxygen, like Earth's, might scatter light one way. An atmosphere thick with carbon dioxide, like Venus or early Mars, might scatter it differently. Dust particles, water vapor, methane, all would affect the color and opacity of the sky. If Proxima B's atmosphere contains a lot of dust or haze, the sky might glow with a diffuse reddish light, the sun itself obscured by thick clouds. Or if the atmosphere is thin and clear, the sky might be nearly black even during the day, with stars visible overhead despite the presence of the sun. During a stellar flare, the sky might brighten suddenly, flooding with light as the star unleashes its fury. For a few minutes or hours, the world would be bathed in harsh, searing brightness. The landscape illuminated as if by a giant flashbulb. Then the flare would subside and the dim red glow would return, leaving the surface cooling and adjusting once again. For any life on Proxima B, these flares would be a regular part of existence. They might happen weekly, daily, or even multiple times per day during active periods. Organisms might have evolved to anticipate them, burrowing underground or retracting into protective shells when the light intensifies. Or perhaps life has adapted to use the flares beneficially. The burst of ultraviolet radiation might trigger photochemical reactions that produce useful compounds. The heat might drive convection currents in the atmosphere or ocean, mixing nutrients and distributing warmth. What seems hostile to us might be essential to alien ecosystems. From the surface of Proxima B, the other stars in the Alpha Centauri system, Alpha Centauri A and B, would be visible in the sky. Because Proxima orbits so far from its two brighter companions, A and B would appear as separate points of light, not as a single fused star. Together, A and B would be the brightest objects in the sky after Proxima itself, shining with a combined apparent magnitude of about -7, far brighter than Venus appears from Earth, perhaps rivaling the brightness of a crescent moon. You could read by their light. They would cast shadows, faint but discernible, adding a second layer of illumination to the landscape. During the planet's night, the side facing away from Proxima A and B would dominate the sky, two brilliant stars close together, an eternal binary beacon in the darkness. For anyone standing on Proxima B, Alpha Centauri A and B would be a constant presence, a reminder that this star system is not isolated, but part of a family. They would never rise or set, always visible in the same part of the sky, their positions shifting slightly over decades and centuries as Proxima slowly orbited around them. And if you could somehow travel from Proxima B to a planet orbiting Alpha Centauri A or B, the view would be reversed. Proxima would be a faint red dot in the distance, barely visible without a telescope, easy to overlook among the countless other stars. But if you knew where to look, you could find it a dim ember marking the location of another world, another piece of this cosmic family. It would be strange and wonderful to think that two worlds in the same star system could be so different, one bathed in golden sunlight from a sun-like star, the other illuminated by the dim red glow of a dwarf. Yet both would share the same stellar ancestry, born from the same clouds of gas and dust, siblings separated by distance, but bound by gravity. Now, let's drift toward the future. Suppose humanity does send a mission to Alpha Centauri. What would we hope to find? Certainly, we'd want to study the stars themselves, their composition, their magnetic fields, their behavior over time. We'd want to map the planets, analyze their atmospheres, search for signs of water and organic molecules. But beyond the science, there's something deeper. Visiting Alpha Centauri would be a symbolic milestone, a declaration that humanity has become a truly spacefaring species. It would mark the beginning of our expansion beyond the solar system, the first step toward the stars. And if we found life, any form of life, even microbial, it would answer one of the oldest questions we've ever asked. Are we alone? The answer would reshape philosophy, religion, science, and culture. It would change how we see ourselves and our place in the universe. It would be, in every sense, a turning point in human history. Let's think about what we would send on such a mission. If we could only carry a small payload, what would we include? Cameras, certainly. Multiple cameras with different focal lengths and wavelengths, capable of capturing visible light, infrared, and ultraviolet. These would give us a complete picture of what the planets look like, from wide-angle context shots to detailed close-ups of surface features, spectrometers to analyze light and chemical composition. By breaking light into its component wavelengths, spectrometers can reveal what elements and molecules are present in a planet's atmosphere or on its surface. They could detect water vapor, oxygen, methane, carbon dioxide, any gas that absorbs or emits light at characteristic wavelengths, magnetometers to measure magnetic fields. These instruments would tell us if Proxima B or other planets have protective magnetic fields and how strong they are. They could also map the magnetic fields of the stars themselves, revealing details about their internal structure and activity. Instruments to detect radiation, particles, and gravitational effects. Radiation detectors would measure the intensity of X-rays and other high-energy radiation from stellar flares. Particle detectors would count protons, electrons, and other charged particles streaming through space. Gravimeters would measure tiny variations in gravitational pull, potentially revealing hidden moons or dense regions within planets. Perhaps a small lander capable of touching down on Proxima B. If the mission could slow down enough, the lander would need to be robust, designed to withstand the impact of landing on an unknown surface. It might carry a drill to collect soil samples, a weather station to measure temperature and atmospheric pressure, and a seismometer to detect quakes and study the planet's interior. Once on the surface, the lander would have only a limited time to gather data before its power ran out. Solar panels wouldn't work well under the dim red sun of Proxima, so it would likely rely on a small nuclear power source, similar to the radioisotope thermoelectric generators used on Mars rovers. Every measurement, every image, every data point would be precious, transmitted back to Earth at the speed of light, arriving over 4 years later to be analysed by scientists who might not even have been born when the mission launched. We might include a message, a record of humanity, like the golden records carried by the Voyager probes. Music, images, greetings in hundreds of languages, a map showing our location in the galaxy, scientific information encoded in a universal format, diagrams of atoms, mathematical constants, the structure of DNA, a pulsar map showing Earth's position relative to known pulsars. The message would be both a greeting and a time capsule, preserving a snapshot of humanity for potential discovery by alien intelligences or by future humans who might one day visit the probe's resting place. But what would we say in such a message? How do you represent an entire species, an entire world, in a format that could be understood by beings we've never met? The Voyager records included sounds of Earth waves crashing, birds singing, thunder rumbling. They included music from different cultures and eras. Bach, Beethoven, Chuck Berry, traditional songs from around the world. They included greetings in 55 languages, from ancient Akkadian to modern Mandarin, and they included images, 115 pictures showing Earth's diversity, from landscapes to cities, from individual humans to groups, from anatomy diagrams to mathematical formulas. A message to Alpha Centauri might follow a similar approach, but updated for modern times. It might include images of Earth taken by satellites, showing the planet in exquisite detail. It might include recent scientific discoveries, gravitational waves, exoplanets, the structure of the cosmos as we understand it now. It might include digital data, text files, audio files, video files encoded in formats explained by diagrams on the physical medium itself. Anyone encountering the probe would first need to figure out how to read the data, using the diagrams as a kind of Rosetta Stone. And it might include an invitation. Not to visit Earth spanning 4 light years is beyond our current capability, and likely beyond theirs as well, but to communicate, to send a signal back, letting us know they received the message, that they're out there, that we're not alone. It would be a message in a bottle, cast into the cosmic ocean, hoping that someone, somewhere, might find it and know that we existed. Now, let's consider the night sky from Earth. Alpha Centauri, that bright, yellowish star, has been a guidepost for Southern Hemisphere travelers for millennia. It's part of the constellation Kentaurus, near the Southern Cross. The constellation Centaurus itself is steeped in mythology. In Greek legend, centaurs were creatures with the upper body of a human and the lower body of a horse. Most centaurs in the myths were wild and savage, prone to violence and drunkenness. But one centaur stood apart, Chiron, the wise teacher who mentored heroes like Achilles and Hercules. Chiron was learned in medicine, archery, and music. He was immortal, yet he suffered a tragic fate, struck by a poisoned arrow. He endured unending pain, unable to die, yet unable to heal. He eventually gave up his immortality to end his suffering, and Zeus placed him among the stars as the constellation Centaurus. In Arabic, the system is sometimes called Rigil Kentaurus, meaning the foot of the centaur. Whether Alpha Centauri represents Chiron's foot or some other part of the celestial centaur varies by interpretation, but the connection to this ancient myth has persisted for thousands of years, linking the star to stories of wisdom, suffering, and transcendence. Ancient mariners used it to navigate, astronomers used it to calibrate their instruments. Poets and storytellers wove it into myths and legends. To the Khoisan people of southern Africa, Alpha Centauri and its neighbours were known as the two men that were lions, celestial hunters, forever pursuing game across the sky. The stars were woven into stories passed down through generations, part of a rich oral tradition that connected the people to the land and the heavens. In Australia, Aboriginal cultures saw the stars as ancestral beings, part of the dream time, the timeless realm of creation and spirit. Alpha Centauri was part of those stories, embedded in the landscape of the night. Different Aboriginal groups had different interpretations, some seeing the star as a campfire, others as an animal or ancestor. These stories remind us that the stars are not just objects of scientific study. They're part of the human experience, woven into our cultures, our histories, our sense of wonder. For ancient astronomers, Alpha Centauri was simply a bright star, notable for its brilliance but not particularly special. It wasn't until the invention of the telescope that its true nature began to be revealed. In 1689, a Jesuit priest named Jean Richaud was observing a comet from Pondicherry, India, when he noticed something unusual about Alpha Centauri. Through his telescope, what appeared to be a single star to the naked eye resolved into two distinct points of light, Alpha Centauri A and B. This was one of the first binary star systems ever discovered, and it sparked curiosity among astronomers. How common were such systems? Did the two stars orbit each other, or were they simply aligned by chance? Over the following decades and centuries, astronomers carefully measured the positions of A and B, tracking their motion across the sky. They confirmed that the two stars were indeed orbiting each other, bound by gravity in a cosmic dance that had been ongoing for billions of years. The discovery of Proxima Centauri came much later. In 1915, astronomer Robert Innes was working at the Union Observatory in Johannesburg, South Africa, when he discovered a faint red star close to Alpha Centauri in the sky. At first, it wasn't clear if this star was actually associated with A and B, or if it was simply a chance alignment. Innes named it Proxima Centauri, nearest star of Kentaurus, because his measurements suggested it might be slightly closer to us than A and B. Over time, astronomers confirmed that Proxima is indeed the closest star to the Sun, and that it shares the same motion through space as Alpha Centauri A and B, strongly suggesting they're all part of the same system. For much of the 20th century, Alpha Centauri remained a curiosity, a nearby stellar system useful for studying stellar properties and dynamics. But the discovery of exoplanets changed everything. Suddenly, our neighboring stars weren't just distant suns, they were potential homes for other worlds, perhaps even other life. The first exoplanet orbiting a sun-like star was discovered in 1995, a Jupiter-sized world orbiting the star 51 Pegasi. That discovery opened the floodgates. Thousands of exoplanets have since been found, orbiting stars of all types, at all distances, in configurations both familiar and utterly alien. And the discovery of Proxima Centauri B in 2016 was a milestone, the closest exoplanet ever found, a potentially habitable world right on our doorstep. From Earth, Alpha Centauri appears as a single yellowish star, one of the brightest in the night sky. But only from the southern hemisphere can you see it well. Those living north of about 25 degrees latitude will find it perpetually below the horizon, forever out of view. For those who can see it, Alpha Centauri is part of a striking region of the sky, near the Southern Cross, a constellation that itself has served as a navigational aid for centuries. Together, Alpha Centauri and the Southern Cross form a distinctive pattern, unmistakable once you know where to look. On a clear night, away from city lights, Alpha Centauri shines with a steady, golden light. It doesn't twinkle as much as some stars do, because it's so bright that atmospheric turbulence doesn't affect it as strongly. It appears calm, serene, a beacon in the darkness. And now, knowing what we know, that it's a triple system, that it has planets, that one of those planets might be habitable, looking up at Alpha Centauri feels different. It's not just a distant point of light anymore. It's a place, a destination, a horizon waiting to be explored. And now, as we stand on the threshold of a new era, Alpha Centauri takes on new meaning. It's not just a distant sun, it's a destination, a challenge, a promise. Let's think about the silence of space. Between Earth and Alpha Centauri lies an unimaginable void, trillions of miles of near-perfect vacuum. There's no air to carry sound, no medium for vibrations. If you could somehow float in that emptiness, you would hear nothing. Not the hum of engines, not the rush of wind, not even your own breath. If you weren't wearing a spacesuit, just silence. Perfect, absolute silence. And yet, that silence is not empty. It's filled with radiation, light from distant stars, cosmic rays from supernovae, the faint afterglow of the Big Bang itself. Magnetic fields thread through the void, shaped by the currents of charged particles flowing from stars. Space is silent, but it's alive with invisible forces. A spacecraft crossing that void would be utterly alone, more isolated than any human has ever been. The nearest help would be years away, moving at the speed of light. Any malfunction, any failure, would have to be solved by the onboard systems, or not at all. It's a daunting thought, and a humbling one. The universe is vast, and we are small, but we reach out anyway, driven by curiosity and hope. Now, let's think about time. A journey to Alpha Centauri would take decades, even at relativistic speeds. For those aboard a spacecraft, time would pass strangely. According to Einstein's theory of relativity, time slows down for objects moving at high speeds relative to a stationary observer. If a spacecraft could reach 90% the speed of light, time aboard the ship would pass more slowly than time on Earth. A journey that takes 40 years for people on Earth might feel like only 20 years to the crew. This is called time dilation. And it's not science fiction, it's real. Confirmed by countless experiments, astronauts aboard the International Space Station age slightly slower than people on the ground, though the difference is measured in milliseconds. For interstellar travelers, the effect would be far more pronounced. They would arrive at Alpha Centauri younger than they would have been if they'd stayed on Earth. But there's no escaping the subjective passage of time. 20 years is still 20 years. No matter how you measure it, the crew would still age, still change, still live through those decades. And when they returned to Earth, if they ever did, they would find a world transformed. Decades would have passed back home, perhaps centuries. Everyone they knew would be older, or gone. The world they left would be a memory, replaced by a future they could barely recognize. This is the cost of interstellar travel. Not just the energy and the engineering, but the time, years, decades, lifetimes spent crossing the void. Let's drift to the stars themselves again. Stars are born in clouds of gas and dust, collapsing under their own gravity until the pressure and temperature at their cores ignite nuclear fusion. Hydrogen atoms fuse into helium, releasing energy in the form of light and heat. Alpha Centauri A, B, and Proxima were all born this way, though probably not together. Proxima Centauri may have formed elsewhere in the galaxy and been captured by the gravity of A and B, or it may have formed from the same nebula and simply drifted far from its siblings. We don't know. The history of stars is written in their motion and their composition, but reading that history is difficult. What we do know is that stars like Alpha Centauri A and B will eventually run out of hydrogen. When that happens, they'll swell into red giants, bloating to many times their current size. Any planets too close will be engulfed, consumed by the expanding star. Eventually, the outer layers of the star will drift away, forming a planetary nebula, a glowing shell of gas illuminated by the hot core left behind. That core will cool and fade, becoming a white dwarf, a dense remnant about the size of Earth. Proxima Centauri will skip the red giant phase. Red dwarfs are too small to expand that way. Instead, Proxima will simply grow dimmer over trillions of years, eventually becoming a black dwarf, a cold, dark cinder, no longer shining. But that future is unimaginably distant. For now, Alpha Centauri shines, and will continue to shine for billions of years. Let's imagine the view from space, looking back at the solar system from Alpha Centauri. The sun would appear as a bright yellowish star, visible in the constellation Cassiopeia. It would be one of the brighter stars in Alpha Centauri's sky, but not the brightest. If you knew where to look, and you had a powerful enough telescope, you might be able to see Earth, a pale blue dot, impossibly small, orbiting that distant star. Carl Sagan famously described Earth this way: seen from the edge of the solar system. From Alpha Centauri, Earth would be even more fragile, even more precious. That pale blue dot is home. It's where every human who has ever lived was born, lived, and died. It's where all our history unfolded, all our triumphs and tragedies, our loves and losses, our wars and peace. Seeing it from such a distance reminds us of how small we are and how rare our world might be. Now, let's think about the sound of silence again, but differently. Not the silence of space, but the silence of waiting. Waiting for data from a distant probe. Waiting for a reply to a message sent across the stars. Waiting for the technology to catch up to our dreams. Patience is the currency of interstellar exploration. Everything takes time. Decades, centuries, millennia. We plant seeds we will never see grow. But that's part of the beauty of it. We reach toward the future, knowing that the answers we seek might not come in our lifetimes. We do it anyway, because the questions matter. Let's turn our thoughts to the Fermi paradox, named after physicist Enrico Fermi. The paradox goes like this: the universe is vast and old. There are billions of stars in our galaxy alone, many with planets, some potentially habitable. If life is common, and if even a small fraction of life develops intelligence and technology, the galaxy should be teeming with civilizations. So where is everyone? This question has haunted scientists for decades. Possible answers range from the hopeful to the unsettling. Maybe intelligent life is rare. Maybe the leap from single-celled organisms to complex, technological civilizations is so improbable that it's only happened a few times in the entire galaxy. Maybe intelligent life is common, but short-lived. Civilizations might destroy themselves through war, environmental collapse, or other catastrophes before they can colonize the stars. Maybe they're out there, but staying quiet. Perhaps advanced civilizations avoid broadcasting their presence, wary of attracting attention from potential threats. Or maybe they're so advanced that we simply don't recognize their presence. We're looking for radio signals and spaceships, but they might communicate in ways we can't detect, using technologies we can't imagine. The Alpha Centauri system, being so close, is a natural place to test these ideas. If intelligent life exists anywhere nearby, it might be there, but so far, the silence persists. Now, let's drift to the sheer scale of stars. Alpha Centauri A has a diameter of about 1.2 million miles, slightly larger than the Sunday. If you could place it where the Sun is, it would fill nearly the same space in our sky. Alpha Centauri B is a bit smaller, about 865,000 miles across. Proxima Centauri, the smallest, is only about 120,000 miles in diameter, roughly 1/7 the size of the Sun, but still far, far larger than Earth. Even the smallest stars dwarf planets. Jupiter, the largest planet in our solar system, is about 86,000 miles across. Proxima Centauri could fit Jupiter inside it, with room to spare. And yet, on cosmic scales, even stars are tiny. The distances between them are so vast that if you shrank the Sun to the size of a grain of sand, Alpha Centauri would be another grain of sand about 4 miles away. Space is mostly empty. The stars are islands in an ocean of darkness, separated by distances that make even light seem slow. Let's imagine sending not a probe, but a signal, a deliberate, structured message aimed at Alpha Centauri, announcing our presence and inviting a response. What would we say? How do you communicate with an intelligence that might be utterly alien, with no shared language, no shared culture, no shared biology? Scientists have proposed using mathematics, which might be universal. The ratio of a circle's circumference to its diameter is pi, roughly 3.14159, regardless of who's calculating it. Prime numbers, numbers divisible only by themselves, and 1 are another universal concept. A message could start with simple mathematical sequences to establish that it's artificial, not a random natural phenomenon. Then it could build from there, using images, diagrams, and patterns to convey information about Earth, humanity, and our place in the galaxy. But even if the message is perfectly crafted, there's no guarantee anyone will receive it, or understand it, or care enough to respond. Still, the act of sending it matters. It's a gesture of hope. Now, let's think about what would happen if we did receive a response from Alpha Centauri. The signal would travel for over 4 years before reaching Earth. By the time we detected it, the beings who sent it might have changed, or moved, or even ceased to exist. The message itself might be incomprehensible at first. It would take teams of scientists, linguists, mathematicians, and cryptographers to decode it, assuming it could be decoded at all. And once we understood it, what then? Do we reply? Do we share the information with the world, or keep it secret? Do we prepare for contact, or brace for conflict? These questions have no easy answers. But they're worth asking, because the universe is vast, and we are listening. Let's drift toward the end of this journey now, gently bringing our thoughts back from the stars. We've wandered through the Alpha Centauri system, from its binary suns to its dim red companion, from the rocky surface of Proxima B to the silent void between. We've imagined the challenges of reaching those distant shores, the patience required, the ingenuity, the courage. We've wondered about life, intelligence, and the vast, lonely stretches of space that separate us from our neighbors. And now, as the facts settle like stardust, it's time to rest. Alpha Centauri is more than just a star system. It's a mirror that reflects our hopes and fears about our place in the universe. When we look at Alpha Centauri, we're asking questions about ourselves. Are we alone? Can we survive beyond our home world? Do we have the wisdom and the will to become a spacefaring species? These are not easy questions, and Alpha Centauri doesn't provide easy answers, but it gives us something to reach for, a destination close enough to imagine achieving, yet far enough to test the very limits of our ingenuity. The journey to Alpha Centauri, whether physical or intellectual, is part of a larger human story. The story of exploration, of pushing boundaries, of refusing to accept that the world ends at the horizon. Our ancestors crossed oceans in wooden boats, not knowing what lay beyond. They climbed mountains because they were there. They looked up at the moon and dreamed of touching it. And decades ago, they did. Now we look at Alpha Centauri, and we dream of touching the stars. Perhaps one day, centuries or millennia from now, humans will stand on a world orbiting Alpha Centauri. They'll look back at the sun, a bright yellow star in their sky, and they'll know that that's where humanity came from. They'll know the long journey that brought them there, the generations who lived and died on the voyage, the sacrifices made to plant the seeds of a new home among the stars. And perhaps they'll look up at other stars in their sky, stars we can only dream of now, and they'll wonder what lies beyond. The cycle will continue, each generation reaching a little farther, exploring a little deeper, driven by the same curiosity that brought us here. We don't know what the future holds, but we do know this. Alpha Centauri is there, shining in the night, a beacon and a promise. It reminds us that the universe is vast and full of possibilities, that we are part of something far greater than ourselves. Alpha Centauri will be there tomorrow, and the day after, and for billions of years to come. It's not going anywhere. The stars are patient. You are part of this story too. The atoms in your body were forged in stars, scattered across space by ancient supernovae, and gathered here, on this small planet, to become you. The iron in your blood was created in the heart of a dying star. The calcium in your bones, the carbon in your cells, the oxygen you breathe, all of it came from the stars. When you look up at Alpha Centauri, you're looking at the same universe that made you. You're made of stardust. Literally and truly, you are the universe looking at itself, contemplating its own vastness, wondering about its own mysteries. In a very real sense, when we explore the universe, we're exploring ourselves. When we ask questions about what's out there, we're asking questions about what's in here, about our origins and our nature and our potential. Alpha Centauri is a chapter in that exploration, a stepping stone on a journey that has no end. Whether we reach it physically or only in our imaginations, it represents something essential about what it means to be human. The drive to look beyond, to ask, what if, to dream of touching the stars. So let that sink in, gently. Let the wonder of it settle into your thoughts, softening the edges of worry, quieting the noise of the day. You are here, on this pale blue dot beneath a sky full of stars, part of an unfolding cosmic story that stretches back to the beginning of time and forward into an unknowable future. And for now, that's enough. The stars will be there, shining in the darkness, waiting for us to grow and learn, and finally reach out to touch them. And somewhere, perhaps on Proxima B or some other world we haven't yet discovered, life might be looking up at its own stars, wondering if it's alone, wondering if there's anyone out there looking back. Maybe one day we'll answer that question. Or maybe we'll discover that we truly are alone, that life is so rare and precious that Earth is the only place it has ever bloomed. And that too would be a kind of answer, a reason to cherish what we have, to protect this fragile oasis in the darkness. Either way, the journey continues, the questions persist, and the stars keep shining, inviting us to dream. Let your breath slow. Let your body relax, sinking into comfort and warmth. Let your mind drift like a spacecraft gliding through the silent, dark, peaceful and free, unburdened by the weight of the day. The cosmos is vast, and you are small, but you are here, and you are part of it all, woven into the fabric of space and time, connected to everything that has ever been, and everything that ever will be. That connection doesn't end when you close your eyes. It continues, always, as constant and eternal as the stars themselves. Sleep well, dreamer, and thank you for wandering among the stars with us tonight. The universe will be waiting for you tomorrow, full of mysteries yet to be explored, questions yet to be answered, horizons yet to be reached. But for now, rest. Let the stars watch over you. Let Alpha Centauri shine in the distance, a reminder that there is always something beyond, always another frontier, always another dream. Good night.